Good afternoon, everyone. Thank Chairman for introducing me. Thank you so much for giving me this opportunity. I'm Eriko Yasunaga from the University of Tokyo. In this presentation, I'll be talking about the assessment of mango quality and evaluation of distribution environment. As you all know, the sustainability, this one? So, as you all know, the Sustainability Development Target 12.3 states to help per capita global food waste, the retail and consumer level, and reduce food losses along production and supply chain, including post-harvest losses by 2030. So food losses and waste are categorized into 5 areas within the food supply chain of fruits and vegetables, and the amount of each segment is estimated. As shown in bottom graph, this one, the food loss and agricultural product occur at about 40 to 50% of production in all regions. Losses in agricultural production dominate for all these industrialized country regions, mostly due to post-harvest fruits and vegetable grading caused by quality standards set by retailers. Waste at the end of food supply chain, consumption is also substantial in all these regions, with 15 to 30% of purchase by mass discarded by consumers. In other developing regions, losses in agricultural production dominate total losses through the food supply chains. Losses during post-harvest and distribution states are also severe, which can be explained by deterioration rate of perishable crops in the warm and humid climate of many countries, as well as seasonality that leads to unsellable gluts. So this is first, I'd like to talk about mango in Japan. This table shows the imported mango to Japan in 2022. Regarding imported volume, the first country is Mexico. The second one is Vietnam. The third one is Peru. A comparison of the unit price of mango fruits imported to Japan shows that the mango from Taiwan is the highest price. So this is Japan also exports mango fruits to several countries, notably Hong Kong. The trading volume is very low, but the unit price very high, so like that. So in addition to reduce food losses, it is extremely important to provide high quality agricultural products and increase their added value. So expensive, yes. Building a food value chain means creating a food-based value-added chain by linking agriculture, forestry, and fishery products while increasing the added value at each stage from production to manufacturing, processing, distribution, and consumption. In other words, connecting the commitment of the production area to the consumer. So this framework is important to the provider of physical input, such as the seed as production level or packing material at the processing level, and the provider of non-financial service, such as field spraying, storage, transport, laboratory testing, management training, market research, and so on. So now, so let me finish about this for now. I'd like to move on to outline my research topics. My special is post-harvest technology that to reduce food losses and contribute to the construction of food value chain. I have focused my attention primarily of two topics. One is the visualization of the quality of vegetables and fruits, and the other one is the optimization of the packaging design of agricultural products during transportation. In this presentation, I will introduce the first topics. So let me briefly explain why I decided to develop the quality visualization model to predict quality change during transportation. Since the 2000s, Japan has faced a number of food-related problems, such as mislabeling of origin and the misuse of agricultural chemicals. Food quality control in Japan is already strict, but the above issues, the consumer awareness of food safety have led to further tightening of quality control. To address these issues, the Japanese government has introduced the GAP, and GDP, and traceability system into the food supply chains. Current traceability system can track information about cultivation, such as the harvest data, and provide the fertilization and the pesticides. However, consumers also need to information and post-harvest distribution practice. Post-harvest distribution practice and their impact on product quality. Therefore, in order to disclose quality information to consumers, it is necessary to establish a model to predict the impact of the fruits and vegetable distribution condition on quality deterioration. Let me give you the procedure for quality visualization. For this topic, we define two nutrition contents as quality indicators: total sugar and vitamin C. First, respiration rate and nutrition contents were measured at various temperature, oxygen concentration, carbon dioxide concentration with stretch period respectively. Next, we built a prediction model for respiration, and then we constructed quality change prediction model that extended the respiration rate prediction model because respiration is closely related to quality deterioration. Therefore, it is necessary to clarify the relationship between accumulative respiration rate and quality change. Then finally, we validated the model to see if it can predict quality change. At first, I will show the evaluation of distribution environment. This figure shows the actual distribution environment mango fruit during transportation from Thailand to Japan. The left figure shows a vibration variation profile, and right one shows the temperature and relative humidity variation profile. The upper one is by zip. Bottom one is the by air shipment. The variation in environmental condition was observed to be greater during transport by truck than during transport by ship or air. Additionally, temperature are maintained at optimal storage temperature during ship transportation, like this. So, comparing the vibration profile at the domestic transportation in Thailand, the vibration from plow was higher than from Pisan Rock area. So, and the ethylene is the most important role for ripening for mango. So we want to check the ethylene concentration at the distribution condition. So we propose a combined sensor device like this. So this one is the obtain the testing which can this equipment can detect the ethylene concentration and the carbon dioxide concentration and temperature and relative humidity. So, but this sensor pack in the commercial box of mango and set via normal air distribution route from packing house in Thailand to the port of entry in Tokyo. I'm sorry. So this is the result of the measurement by the system. The CO2 increased considerably during shipment, especially between 10 to 17 hours due to respiration of the fruits. After 16 hours later, a sharp spike was observed in ethylene concentration. After initial stabilization, temperature and relative humidity remained relatively consistent. Usually, it took three days totally by air from Thailand to Japan, but this system cannot detect all the distribution condition because the battery shortage. So now, now the portable and high-end one is like that the equipment. So now we want to develop the more portable and useful equipment we need to know the real distribution condition. So in particular, 3 measurement technology have shown the promising potential for fruit supply chain and were tested to develop robust portable monitoring system, non-dispersive infrared spectroscopy, electrochemical measurement, and nanoparticle semiconductors. So now we try to develop the sensor. So this one is the number of viable bacteria in soil and irrigation water was also investigated in mango field in 3 regions of Thailand. Although Salmonella and E. coli were detected in some of mango fields, the general viable bacteria count were low in all fields, indicating the frequency of detection of microorganisms that pose a problem in terms of food hygiene was low. Sorry. So next topic, I will introduce assessment of mango quality. So at first, this slide shows the schematic diagram for measuring respiration rate. So we measured respiration rate of 3 fruits at the same instant of different storage temperature by flow-through method. The air discharged from the compressor is sent to the chamber for measuring the respiration rate by controlling the flow rate with the mass flow controller, like this. The carbon dioxide concentration is measured using carbon dioxide analyzer, then we calculate respiration rate. This figure shows the change in respiration rate of mango fruit stored at 10 and 25 degrees Celsius. The respiration rate was restrained with the decrease in storage temperature. In the fruits stored at 25 degrees, the respiration increased from the second day after the start of storage, and climacteric rise was confirmed on the 5th day. On the other hand, the fruit stored at 10 degrees was finally stored for more than 30 days, but no climacteric was confirmed because the mango fruit is chilling sensitive fruit, so the under 30 degrees they cannot continue the ripening, so they cannot appear climacteric rise. So this figure illustrates the change in accumulative respiration rate of mango fruits stored at 10 and 20 degrees Celsius. The accumulated respiration rate, the fruit stored at 25 degrees for 2 days, and was equivalent the fruit stored 10 days for 6 days. So this figure illustrates the change in respiration rate between accumulative respiration rate and the fruit's quality. Like the fruit's quality indicator is hardness, and the bricks and acidity, and the ratio bricks and acidity. So all of the indicator, until ripening begins, the accumulated respiration rate and quality after harvest are same regardless of the storage temperature. But after ripening, the relationship between integrated respiration rate and quality varied with temperature. This figure shows the variation of respiration rate with elapsed time, with several temperature, and the right one is the relationship between accumulative respiration rate and hardness score. These figures indicate even if the storage temperature are different, we can find the high correlation between accumulative respiration rate and hardness score. This result was similarly demonstrated for peel color. So Japan has a very low food self-sufficiency rate of 38%, and it depends on imported food. We are also conducting a research food loss and long-distance transportation, such as import and export, because the percentage of food losses is high in such long distribution. This is example of mango exported from Thailand in Japan. And in Japan, mango are produced in Okinawa. Here is a comparison of two. This slide shows the fruit's appearance before and after distribution. Harvest site are Plough Pison Rock in Thailand and Okinawa in Japan. Before distribution were like this. Then good and bad example after distribution were like these. The incidence of fruits quality degradation shows such value. In distribution condition by SIP, ripening mango become ripened mango after 3 weeks after imported to Japan. However, there is room for improvement in the distribution environment and packaging material because of some mango damage which are browning in the shape of the kelp of suffered from cold injury. So mango fruits are highly sensitive to room temperature. So we store the almost 50 degree by the ship straight transportation. So the can cause chilling injury if shoot temperature below 30 degrees Celsius. In shipping from Thailand, it is stored 15 degrees Celsius during transportation. Unfortunately, the taste of mango transported by ship from Thailand to Japan was different from that the mango eaten in Thailand, with strong sour taste. This was thought to be result not being able to ripen properly due to be stored and transported at 15 degrees Celsius. Therefore, it was confirmed that we will change the arrival, before arrival day, stored temperature rising the 25 degree for suitable ripening. So we will improve the quality like this. So the sour is the disappear and the sugar acid ration is the like this change. So we can, therefore it was confirmed that the taste would be improved by heating the mango at 25 degrees, the optimum temperature for ripening, for 2 days before arriving in Japan. So when predicting quality, I introduced a prediction model to use the theoretical formulation, but there is also method to use the machine learning. This shows as in example of prediction of the internal quality from the skin color of the fruit using machine learning technique called random forest. So we will use the peel color, then we will predict the fruit's quality like hardness, L-ascorbic acid, and total soluble solid. So this figure shows the model accuracy. The random forest model were able to link the peel color parameter to each of the fruit's quality parameters during post-harvest ripening. So this is the just example for the packaging design simulation model. So it's using for peach fruits. So this model can using like this equation. So we can calculate the how strength to added for peach or absorb the fruits cap, absorb the strength. And for example, so we can this information can predict the end packaging design modeling is very useful. This is the let me summarize my talk. In the first research topic, I established a model that enable quality assessment of agricultural products and visualization of quality information through monitoring of the distribution environment. Through this study, I believe that we can contribute to the reduction of food loss and the establishment of food value chain. That's all. Thank you very much.